Okay, so hi everyone. Welcome to this talk. Thanks for staying on this room. I know it has been a long day and we would probably be a little bit tired, but I promise this is not going to be one of those very heavy talks about functional programming. I'll try to be like very descriptive about everything. And okay, let's just start. Let me introduce me like very briefly. My name is Jorge. I am part of 47 Degrees, which is a software consultancy like very focused on functional programming. So we work for client companies where we kind of integrate our engineers within their teams, and we try to help them to reach their deadlines and to meet their goals. And we are particularly focused on functional solutions. We are covering all the platforms like backend, front-end web, also mobile. So if your company is interested on this paradigm, please feel free to ping us. So this would probably be like the first question I will make to myself if I wanted to start doing functional programming over a language like Kotlin. Can we consider Kotlin a functional language? Or what does it mean, right? So let's peek into the features of the language to take a look at what's available there. One of the most important features is probably the high-order function support, at least to me, because that's kind of unlocking thinking about functions as if they were values. So you can actually pass functions around as arguments, return functions as other function results. You are actually able to store functions in variables and then running them later on, right, at runtime. So you can kind of start reasoning about your code as if it was a composition of functions, right, or computations, we could say. So that's probably the most important one here on this list. But there is also support for things like immutability, as you can see there. You have this val modifier that you can apply over the properties of a data class or a class. So you have the chance to create your immutable models there. So the language is kind of open to it. It's not enforcing you to work with immutability, but you totally have that chance. And then there is something that in the functional world we call the algebraic data types, which is just like a fancy word to refer to seal classes and data classes, okay? In the functional programming world, it's pretty common to use this, the combination of both things to kind of model your business logic. So you're able to kind of model all the operations that your business is able to perform using algebraic data types, okay? Those are seal classes, data classes. The seal class would be a sum type because it's this scenario where you have like a closed hierarchy of possibilities and you need to pick a single one. And the product type is the data class because the data classes lives up to its properties, right? So it's like the product of its properties. Those are pretty used in functional world, so it's kind of also really nice to have to achieve what we want. There's also a feature in the language which is expressions. So expressions are kind of enforcing you to return something from the code block, which that's pretty cool and very on the line of functional thinking, because when you're doing functional, you really try to get a return value from all your functions, right? You don't really like those functions that are returning unit, because unit means that you are actually performing a side effect there. Don't worry, we'll know what's a side effect pretty soon. So it's looking good, but is it enough to do what we call type functional programming? I don't think it is. I mean, if we really want to go for type functional programming or type pure functional programming, we need higher order abstractions like the type classes and higher kinds. Don't worry, because we don't really need to know what those are on this talk. And that's kind of the beauty of the framework I'm about to talk about. You don't need to dig in to those to understand or to be able to write your own functional programs, okay? But to get that working, you actually need those. So something on top was needed. And that's why we started thinking about creating something like Arrow. It was probably like about 2 years ago, when we started creating the library, like adding the very initial data types and so on. And then it started growing like very gradually from that point in time and until what it is today, which is a very inclusive effort that actually started in a very small community, in a Spanish small community. And it's a very inclusive effort that has room for everyone that wants to help, okay? I think that's kind of the power we have, and we are always going to try to keep that, if possible. So Arrow enables the functional paradigm over the language. It's highly modular. As you can see, it can be sometimes a complexity on top of the already existing learning curve for functional programming, because we are providing a lot of different artifacts, and we are actually aware of that. So we are trying to approach to this like in two different ways. The first one would be like for dummies. Please don't take this bad, but it's like for the newcomers. We want to provide like very high-level artifacts. So you just need to import like 2 or 3 artifacts, and then you are ready to go. You have everything built in there, which would be like the ones we got here. If we are talking about the Arrow core, for example, we could provide this one in the first row, which would bring like everything related to the Arrow core inside. For the effects feature, we could do the same. We would have that global one. But apart from that, we also provide more granular artifacts. So you can just go and grab the only parts you need to build your program. So you have kind of the best of both worlds. We are still iterating over this to make it even more clear and explicit for newcomers. But we are totally aware of that and working on it. That's cool, but how can I actually use a framework like Arrow into my daily work? Because that's probably the point here, right? In theory, everything sounds all right, but how can I actually start using it every day? If we think about any program in the world, we'll realize that I've written here the majority of them, but I think it's every program in the world contains side effects, or what we call side effects. Because otherwise, your program wouldn't have any state, or your program wouldn't even render anything in the screen or anything like that. So it would be like dead code or something. So your program has side effects inside, and it needs them. So side effects are like, for example, when I'm querying network, or I'm storing something in a database, or I'm logging something to console, or I'm sending an event to a server, an analytics, a metric system, server side. All those are considered side effects and kind of escape the control of your app business logic. So you need to keep those under control. The problem with those is that those things can provoke, can leverage the percentage of ambiguity, we could say, over your code. You cannot reason about your code in a deterministic way anymore, because if you are calling server, it could fail, it could be slow, it could, I don't know. A bunch of things could happen. So it's not like every time returning the same result for every single time. And when your programs are not deterministic, even if we can live with that in simple systems or simple apps, that's not super cool, because at some point, you are going to get a lot of complexities about when you try to reason about that code, because you can get into things like race conditions, because your app state is being mutated from different states on or places on your architecture. So is there a solution for that? Is it possible to remove side effects at all? I don't think so, right? You need them. But there is a solution in terms of architecture. And this is something we've been doing since long ago, actually. If you try to kind of remove those side effects, or we could also call them implementation details, right? Because we are talking about querying network, or a database driver, or something like that, or the file system. All those complexities can be hidden as implementation details on your architecture, so you just target abstractions all the time. So if you try to remove those implementation details and kind of push them all together to a single point in the architecture, then you are constraining them to that layer, and your whole architecture stays totally pure beyond that point, right? And I say, well, actually, you would try to do that in what we call the edge of the world. That's just, at the end of the day, it's the entry point to your system. So if you're doing Android, for example, it would be the application, or the activity, or the fragment. That's the entry point to your app. It's actually where you compose your dependency graphs when you are using some systems like Dagger, or Kotlin, or Coin. By the way, we have a very interesting talk about Kotlin right after this one, so please come to that one also. And if we are talking about a RESTful API, it could be the controllers, where we are kind of wiring up all those routes to the different static methods for the different endpoints. That's the entry point. For all the programs, it could be the main function for programs that run over the JVM. So overall, it's all about architecture. If we depend on abstractions along the different layers of our architecture and try to push the decision about which implementation details to use to this entry point, as we've always been doing with any other dependency injection frameworks, which is the point where we actually compose the dependency graphs, then we are actually removing side effects to the whole architecture and constraining them to a single place. So you can keep those under control. Let's keep in mind that side effects are actually the implementation details, because if you understand that, then I think it becomes much easier. So if we step back for a second and try to understand what we refer to when we say pure functions. Pure functions is basically when a function returns the same value for the same input arguments every single time. So if I call a function that adds two numbers, 1 and 2, it's always going to return 3. That's not going to change, ever. So if I call the same function 1,000 times, I would get 3 as a result 1,000 times. And that's actually because the function is deterministic. And that's actually enabling or unlocking some approaches like compiler optimizations, because the compiler can then step in and say, hey, I am reading this code source, and wherever we have a call to the add function where we are passing 1 and 2, I can just replace that by 3 out of the box, because I know that certainly it's always going to return 3. If there's ambiguity in the code, you cannot actually apply that optimization, because it's not true for all the cases. What if that function is trying to save that into a memory cache, and then that can throw, like 1% of the times you call it? It's not deterministic anymore. Or if you are trying to send that to an analytics system in the server side, same thing. It could be slow. It could just be canceled. It could fail and introduce ambiguity in many different ways. So let's try to step into some small exercises here to see if we are paying attention, okay? Oh, sorry for this. We don't really want to see that. Cool. So who thinks, I mean, this is a function where we are actually just printing something to console. Who thinks this is pure? Please raise your hands. OK. Not many people. Who thinks this is impure? OK, most of you. Yeah, I think this is probably the most clear case, because we are just calling the side effect right away. So it's going to be, actually, if I run this code snippet, you can see that it prints the hello world to console. So it's a side effect, OK? So how can we make this function pure? Maybe one approach could be to just return a function, right? If you return a function, what you are returning is a computation that is able to print to console. But it's still not run. It's like deferred. You need to actually proactively tell it to run, so it runs. So if I run this, it's just returning the lambda as is. I would need to edit this and actually invoke it, or you can invoke it like this, to perform the side effect, OK? So until the moment I proactively told it to run, it's safe, it's pure, because even if it contains effects, they are deferred in time. They are waiting for me to take the control and decide when I'm ready to run them. And that's pretty important to remember. But there is like a more functional approach to this. Instead of returning a function, we could return the functional data type, IO. IO is just like the same thing. It's like saying, this is a computation that is deferred. It's an IO computation. But you still keep the power to decide when to run it. So it defers execution out of the box. And of course, it fits well in functional data code bases, because it's designed for that. Cool. So we know that. So who knows this is? Who thinks this is pure? You don't look very convinced. OK. And who thinks this is impure? Nobody. And the rest of the people, are you sleeping already? This is pure, OK, because we are actually wrapping our computation, which is the same computation we had before. We are wrapping it into the functional data type, IO, which is deferring the execution of this lambda right away for us. OK? So if I run this, what we get is suspend. Suspend is just one implementation for IO. IO is a seal class. It's the model as a seal class in Arrow. So it's one of its possible implementations and means that it's still waiting for us to run the actual lambda, which is the thunk inside, right? So we keep control over when to run this. Cool. But we have just suspended a computation, right? Why don't we use the support for suspended functions that we get from the Kotlin coroutines standard library, right? We could just mark the function or label the function as suspended instead of wrapping it into IO, and automatically we can remove the IO from there, just keep it as is, and then we could try to run it. But before, who thinks this is pure? OK? All right, and who thinks this is impure? Cool. It's probably like 50-50. There's a little bit more people thinking this is impure, and this is because there's some ambiguity here. I mean, I think all of you know that this is actually going to crash. The compiler is not going to allow you to run this computation like in the environment as is, because it's telling you cannot really run suspended functions without when they are outside of a safe context, or scope for running suspended functions. You need to run them inside of an already suspended context. So the compiler is helping you here to not run your side effects in unsafe environments. That's really important also. So knowing that the compiler is going to help us to get this done, we can get into what we call here the suspended future, which is like the beginning for what we are actually going to showcase today. So if we take a look at the plan bins of coroutines, the stable coroutines that we got in the Kotlin standard library, we find an annotation that is called restrict suspension, as you can see here. That you can put over any class or any scope, we could say, and that automatically creates a safe environment for running suspended functions within that scope, which means if I call a function, this one, print outer hello world, this one on top, which is actually suspended, but it's not defined within the scope of this class, it's going to crash. The compiler is not going to allow you to run a suspended function that has not been defined within my scope, the scope that is restricting the suspension. But in the other hand, if I run this one, that is the print inner hello world, which is defined over that scope, we could actually also define it right inside of this class. That one is actually going to work because it's defined within the scope of the restricted suspension. So if you take a look carefully to this, you will notice that you have the ability, or we have the ability to decide where our side effects can run. So we can decide what's safe and what's unsafe for you. And we can actually create a framework that ensures safety over any possible side effects you write, thanks to this. And it's based on the same thing that KotlinX coroutines are built on top of. So that's where something like ArrowFx comes in. If you take a look to ArrowFx, it's basically what we call pure functional effects on top of Arrow. And it's basically the chance for you to write any possible programs in the world using functional programming without the need to actually know anything about functional programming. You just need to have a clear vision of what's a side effect and why it's introducing it's making your code be non-deterministic anymore. So we got 4 primitives that we are going to use to create any program in the world. Don't worry, we'll go one by one. The first one is fx. This is the block, the code block itself. If you're writing a program or any function in your architecture, you can just straightforward open an FX block, and that ensures that it's going to be a deferred program that is able to contain effects. So it's like saying, this is my program. And the program is actually going to be deferred out of the box for you. But if you run the effects, as we are doing here, right straight in the environment, or right away into the program, we are going to get an error. And we get an error, and this is intended because we want to say, FX is able to contain effects, but you actually need to handle them. So the error is telling you that. You cannot just run this in the environment as is. You need to provide the next primitive, which would be effect, okay? With effect, what you do is effectively wrap in your side effects. And with that, you're automatically saying, hey, this is a side effect. I know that. I'm controlling that. Okay? If you run this, you don't get the error anymore. What you get back from this is a pure computation that contains the effect itself. But there is still something else, right? Because if you look at this is actually not printing hello world yet, so the program is actually not running yet. Okay. It's returning something that is pure. It's a pure computation that has still not run. So you need to call bind for that. Every time you have an effect and you have wrapped it in this effect block for saying this is an effect that I need to control, if you want it to actually run or unfold or unwrap, like perform the actual computation that is inside of it, you need to call bind on it. Bind is actually flag map behind the scenes. It's going to flag map for you. Okay, if you know what's flag map, you have already seen flag maps in other frameworks, and it always takes like the inner value, and then is kind of enabling you to perform sequential computations. Like you get the you resolve the effect, get the inner value, you can use it for the second operation, you force it to resolve, get the inner value, you can use it for the third one. So flag map is designed for sequential computations. And for being able to apply flag map under the hood or kind of resolve that effect, you just need to bind it. We are overloading this operator, the exclamation operator, but this is equivalent to just calling bind like this. Okay, same thing. If you run this, you get a binded effect, but it's still not running, right? This is like saying, hey, this is the program. It has a result inside, but it's still waiting for you to run it. So it's still pure by default. So we got the way to declare programs that are able to contain effects. We got a way to control those effects. We got a way to, or control for the actual execution of those effects with bind. So we decide when it's running and when not. But there is still one thing left, because the whole program is deferred, as we said. And we'll know how to run it. Just as a little parenthesis, you can see here how we are being able to convert a nested amount of flag maps into a single indentation level thanks to bind. If I apply bind to each one of those computations, I enforce it to resolve and then actually extract the inner value and assign it to the left-hand side. And I can use it to perform the subsequent call, which is also enforced to resolve with bind. Then I can get the result and use it for the third one. So I am obtaining this feeling of synchronous code when it's actually asynchronous. And it's removing a lot of complexities when you write code, because you get this single level of indentation and it's easier to reason about. Because it's like operation after operation, right? Like the standard way of how software computations work. Finally, we are ready to run our program that is still deferred in time. So we got our effects block, our side effect that is controlled using this effect keyword, and we are actually enforcing it to run. And then we are in the edge of the world, in the entry point of our system, which is, in this case, this is JVM app, so it's going to be the main function. This is the place where I can run my unsafe side effects, because I want the rest of my architecture playing with pure functions. But this is the only place where I want to actually run it. So I just need to wrap it into unsafe, and that's automatically going to run the program for you. And the Kotlin primitives that you can find in the standard library like run blocking, can still be used with our programs. If I run this, I finally get the hello world. So I've efficiently written a program that is enforcing me to control side effects, because otherwise they would not even compile. And it's totally polymorphic and safe. And I say that this is polymorphic because you can just keep the same structure, fx, the bind, effect for wrapping the actual side effect, but just change the return type to be what we call a higher kind, which is just like an abstraction for a container. This is like saying it's an F container that can be observable, flowable, I/O. It can be whatever data type that is able to support asynchrony and concurrency. Future, deferred. But I don't care about which one is it yet. And this program is automatically polymorphic. I can just decide then at the edge of the wall which is the data type I wanna actually use to run it. I could actually run this program using other data types, not just I/O. I could run it using flowable, observable, mono, or flags from the reactor framework. Any of those data types that support asynchrony and concurrency, that of course we need to provide support for in Arrow, right? When you write polymorphic programs, you are enforced to never target concrete semantics. You cannot use the concrete semantics of ArcJava. You are enforced to play with the higher level semantics that our abstractions provide. So your code is always staying pure and depending on those abstractions. By the way, those abstractions are the type classes, but we don't care much about that here. Cool. Let's talk about what we call fibers. What's a fiber? Fiber is like a lightweight asynchronous process. This is built on top of the same plan beans that coroutine and standard library uses, like suspend and coroutine continuation and those things. The actual KotlinX coroutines library is built on top of that also. So we use this concept of lightweight threads to create our version of it, that we want to have a single representation in our system. So we don't have this kind of ambiguity with different approaches, depending if it's asynchronous or not. I'm going to use these different methods. No, it's going to be the same way for all the cases, because we are targeting abstractions and we don't have those problems. So if we want to do something like this, where we fork our execution flow, like in 3 different fibers, and then we want to join them in the end, which means async await, which means I'm waiting for all the results to be ready to combine in the end, you can do something like this. This is a simpler scenario where we have a single one, but you could do the same for many. So you prepare an operation that is going to be an effect. We are simulating an effect here. We are just printing the thread name to console. And then what we do is pick a non-blocking context and say, start a fiber with this operation, which is like saying, run this operation in a fiber. That's branching my execution flow and running that in a separate fiber. And then I can go and say, fiber that is returned for that by that constructor, join. When you call join, this is like an async await. You are waiting for it to complete. Your code becomes blocking and waiting for that fiber to complete. So I can get the result of thread name and print it, right? So if you run this, you see that it's actually running the fork join pool worker, which is like the thread we are spawning, the fiber we are spawning. Cool, but what happens when you get one of those computations failing? Since you're waiting for all of those to complete, if one of them fails, you should consider the whole operation failed, right? No problem, I mean, you can still use the same start fiber smart constructor, we could say, to spawn the fiber, to fork the execution flow. And then if that operation throws, it doesn't matter, because we can hook an error handling strategy to our fiber, to our operation, which is going to be called. It's a lambda that is going to be called if the computation in the fiber actually fails. As you can see, we are recovering from that error. For races, it's the same thing, but this time we need to call race n over a non-blocking context, which means I'm going to run these operations non-blockingly, so parallelly. That means parallelly. and then I'm going to make them race. I just cared about the first one that is completing in this scenario, right? This is also a common use case. I'm spawning like 3, 4, 10 fibers, and I just care about the first one that completes in this case. So, right, it's going to be the second now. If I run this many times, luckily, right, this is going to return in the first one now. So that demonstrates that it's parallel. The computation doesn't know which one is going to win in the race. You just get the first one. What about in a scenario where we got like n different parallel operations and we need to combine the results in the end? We got something called parmap for that. Parmap-n is basically doing the same. You say, I pick an execution context. I don't want it to be blocking. I want it to be non-blocking, so all computations can run parallelly. And then I just apply a lambda in the end for gathering results. It's a piece of cake, concurrency, in this framework. In this case, I'm using instead of passing a lambda, I'm passing a reference to the tuple3 constructor, but it's a lambda at the end of the day. Because I want to like apply the structuring here so I can access to each one of the values separately. Just a little trick. But you could actually do something like this. Right? So you could actually, oh, sorry, I don't have, my keys are not properly mapping. You can imagine. That's an arrow. So you could do something like this, okay? You just pass a standard lambda instead of that reference to the tuple3 constructor. That means that whenever all the computations complete, the lambda is going to get called, and you can combine results in the end, which is also probably like a pretty common use case in any program. For error handling, because one of those could fail, as we said, and we need to consider the whole computation failed because we need all of them to compose our final result. So for error handling, we can do the same thing. We can just parmap-n, and when one of them is throwing, we can just hook an error handling strategy the same way we did before. Same story, out of the box. So the lambda is recovering from the error for us. It's running the actual lambda when one of the computations is failing. More stuff that you can find inside. You can actually jump threads or fibers arbitrarily, like execution context. You can say, hey, switch to a non-blocking context, then run this fiber, then switch to I/O, then run this fiber, then switch to UI, then run this fiber. Let's see what happens. Right? So you get all the thread switching done by you in an arbitrary way. You get the power to switch back and forth whenever you need. So the first one is going to be the for join pool because it's in a non-blocking thread. The second one is I/O. Sorry, this one is I/O, and the third one is UI, right? Bracket. This is safe resource acquisition. There are a lot of programs where you want to acquire a resource, like this tab. We open the tab, we use the water, but we want to be sure that in the end, the tab is properly closed, right? But we could have an alternative scenario where we actually cancel the operation. In the middle, we get a phone call, and we decide that we are not going to do that anymore. Well, still, we want to be sure that the tab gets properly closed, so we don't leak, right? But what if there's an error? What if I try to use it, there's an error there, the instrument is kind of not ready, and then still in that scenario, I really want to close the tab. I want to be sure that the tab gets closed. You can do that with Bracket. Bracket is a type class that is basically going to ensure that a release callback is being called for each one of those scenarios without any exceptions. This is a wall of code, but in the end, you just need to look at this. Acquire. Acquire is going to be a file that we are opening. That's going to be like the shared resource, or the resource that we want to safely release in the end. We get acquired, we bracket case over it and say, whenever it ends, we pass this release, which is a lambda. Release is all this thing. It's a lambda that is actually going to tell me why did it complete, or maybe not complete, so I can know if it completed, it got canceled, or it throwed an error. And then I can react in different ways to this. And since I am sure that for all the possible cases this lambda is going to get called, I can hook my all my disposables or whatever I need to use for disposing these things, like for closing the tab in this case, or the file on this example. So if I run this, I'm sorry because I need to scroll a bit here. So the first one is like reading the file content, is actually using it, then it completes, and then we ensure that the file gets closed as it should. This is really cool because Bracket is actually able to abstract over how you perform the operation. The operation could actually go to a server and be asynchronous. The type class Bracket is abstracting over that. You just need to reason about this is an operation, and whenever it completes, I need to release the actual resource. So that's powerful. Built-in cancellation. Cancellation is one of probably the most complex problems in concurrency. And we try to provide that out of the box with a single approach for all the cases, right? So cancellation, we decide to spawn or start a fiber over a non-blocking context. And we run this infinite loop that is kind of printing to console on every iteration, okay? First iteration, second iteration, third iteration, right? Then whenever that's running, we wait for 100 milliseconds, and then we print this. I'm tired of waiting. I got my cancel token that the start fiber returned, and bind it. You just need to actually run the cancel token, and then the computation actually gets canceled, okay? This is probably going to print like a ton of results because it's very fast. But in the end, whenever 100 milliseconds have passed, hopefully we can get, there you go, we can get our cancellation. I'm tired of waiting, and then I quit. And we cannot see more iterations of that log anymore. So as you can see, cancellation, which is kind of a hard one, is built inside of this system. You don't need to reason much about it. It's just about binding this cancellation token whenever you are ready to. Abstracts over functionality. Functionality is just like the number of arguments a function has. This is basically saying you can pass n different computations, for example, for the race, or for the parmap that we saw for parallelizing operations. I don't care. You can still apply fold, and you can provide lambdas for each one of them to be called. So if it's the one that completes first, it will actually run the first lambda. Otherwise, it will run the second lambda. Let's see who's the winner here. It's the first one, okay? This is also powerful because you don't need to have like different encodings for handling the different number of arguments. You can have your logic completely agnostic of that. Just pass the n amount of operations to these combinators. Let's also know that you can still use FX for all monads. You don't need to just use IO, which is what we are using under the hood for fibers. You can use other data types, more simple ones like option. There are some alternative binding styles as you saw before. There is this bind one, as you saw, so you can just call it like .bind, which is probably easier to understand or to read. You also have this one, which is using the destructoring support from data classes, so you can actually enforce it to extract the inner value. That's just an alternative syntax for the same thing. It's flat mapping under the hood and returning you the inner value. I'm not sure we are going to keep all of them forever. We'll probably try to conflate in a single one so it becomes easier for the learning curve. So that's all you can. That's all I wanted to tell you about ArrowFx. It can do many more things. There's not going to be time for reviewing all of them, but as you can see, you have the power to do almost whatever you need to do on your programs. You can ensure that you write a program that by design is enforced to control side effects. You can hook error handling strategies. You can do parallelism, so concurrent operations. You can do sequential operations. It's polymorphic, so you can actually run it for different data types. It's very powerful, but with a very direct syntax. About the ecosystem of Arrow, there's the Keep 87. We always mention this. We've been working on a proposal, an official proposal for the Kotlin language that we actually sent like a couple of months ago. And it's about introducing the concept of type classes in the language. That's basically the chance to create families of functions that work over a generic argument. And then if you treat those as dependencies of your program, like for example, a repository is get, set, get all, and all of them work over user or whatever. It's a generic type. You can provide implementations for those type classes at compile time. So you would get like a dependency injection at compile time and verification of dependencies at compile time out of the box, built into the standard library of the language. So you wouldn't ever need to use other frameworks for that. Hopefully that can be merged, but we are still waiting for JetBrains to, there's the code, those are, Thomas and me were the ones writing it. This is what provides, I've already said this, and we are still waiting. It's submitted, but we are still waiting for JetBrains to give us some feedback. They say that they have it in a schedule, but they have tons of priorities, so we can't tell when we are going to be able to keep iterating over it. Okay? Still, we also got other ideas, like we are exploring compiler plugins also, so we wouldn't need to get this into the language. But we feel like it's a powerful feature that is not just related to functional programming, but it's essentially compile time dependency injection. We are actually not even calling these interfaces type classes or anything. They are requirements for your program that can be fulfilled at compile time. But we are also exploring compiler plugins and other strategies for this. There are some libraries incoming for the Arrow ecosystem. There is Helios, which is like a blazing fast serialization library that works on top of Arrow. So if you have an Arrow code base and you want to serialize and deserialize JSON, you can use our Helios for that. There's Collect for automatically batching and deduplicating requests to different sources of data. So if you have memory cache or like different endpoints and you want to be sure that you don't repeat calls and they are automatically cached for you, Collect is going to help on doing that for you. And there are other things coming like the streams library, so you are able to apply this streaming API over Arrow in a functional way, which we can actually use to build Android integrations on top of it, so we can model the whole life cycle of Android using this stream declarative library. Helios was released last week, and please, if you are trying or playing with functional programming, just grab it and give us any feedback you have. Arrow is in Maven Central. You can use it since a long time ago. We are not in stable releases, but it's very stable. But it's still also prone to change in some ways. Actually, all the ArrowFx framework is actually going to change next month, since we are releasing 0.9.1, which has some new goodies added to it. But the port is going to be like very straightforward. So you can already use it. We are targeting for end year for a first stable release of Arrow. We want you in. Arrow is a community effort. We provide all the different channels to contact us. We provide mentoring one-to-one for your given problems. If you are trying to do functional programming and you feel like you don't really see clear how to apply it to your concrete use case, just come into these channels. We are trying to help everyone. And we are also open to grow in terms of maintainers. Okay, I think, as I said before, this is probably the biggest power of Arrow, to stay open to everyone. And that's what made us be what we are today. And I feel like if we keep this approach for 1 or 2 more years, we could have something really important here. And that would be all. I would be open for questions now. Thank you very much. Thanks. Any questions? Nobody? Guillermo, please. Guillermo is also another Arrow maintainer. So
you know what I'm going to ask. What are the plans for Kotlin multi-platform support?
Okay, as I told you before, you are the one responsible to code that, so who knows? Now, being fair, that's intended to be part of the first stable release. We don't want to go to 1.0 without being totally multi-platform. So we are exploring alternative approaches because we are using capt for all the code derivation at compile time, and capt is JVM dependent. And the Kotlin team is not really doing much for making it supporting multi-platform. So we are exploring alternative approaches where we are using our own parser for the PSI and creating our own AST of all the source inputs, and then using that for generating code at compile time, which is very similar to what Amanda was talking about this morning. So hopefully we can find the right approach. We will explore different alternatives, but the 47 Degrees team is putting efforts and resources on that. So hopefully we can be multi-platform before the first stable release. Anyone else? Please.
I'm just curious because of the not operator for bind, because of you are always in an FX context, or in some context you control. Wouldn't it be possible to use a binary function?
Sorry, I didn't understand the question. Can you repeat?
You use the not operator for binding, so that the side effects happen.
Yeah.
So I was just curious if I'm wrong with the syntax, but couldn't you use a binary function, like you control the autotype and you control the bind expression? Couldn't you use a better name than not, like the bind before?
You mean like trying to find some hack to avoid explicitly using bind? So it does it for you?
Or even have a better name. I will try explaining better, I guess, afterwards.
I'm sorry. I'm sorry.
It was my spot, sorry.
It's fine, but we can talk later, so please just catch me and I'll try to answer your question. Thanks.
Do you have some parts in the framework which are for unit tests, so you can write them easily with the function? Because moving every side effect to the edge of the world makes sense for me, especially for testing.
We don't have plans for releasing a testing framework, but I don't think I can discard it. I mean, if at some point it makes sense, we will do it. But for now, we feel like using this type class system, it's very, very easy to inject dependencies, because you just need to create your own. If we get back, sorry, I think I lost control of it. There you go. Where is it? Where is the polymorphism slide? There you go. Here we are using a type class for declaring our whole program. This is an interface. It can be a dependency, or it can be a composition of interfaces. So that's actually the requirements for your program. If you create an extension of that FX type class, you can provide access to all your dependencies there. And you're going to get them automatically passed all the way down for you, because they are part of the receiver of the function. You don't even need to be manually passing them. So using this approach, you can go ahead and in your edge of the world, you can pass the actual instances to use for those dependencies. So it's like very manual, but at the end of the day, it's super simple, and you get those results for you at the end, at every single level of your architecture. So you can actually do testing and replace any piece of your architecture just by using that. But you usually just need to replace the side effects. Yeah, everything else can be just the pure production code, because it's pure, you don't care about using the real one. Even it's better, because you're using the production code as much as possible from your testing environment, which is always good.
It looks like a very pure way of mocking your environment, because your environment is all on the edge, and you can put to it anything
you can do that.
That's great. Yeah.
You can do that, but there's also something else coming for dependency injection that will help that. I think it's coming in 091, where we are going to have more data types, not just IO, but another one which is bio, where we can explicitly say which error types you want to use, not just throwable. And then there is another one which is like envio or something like that, which is actually prepared to inject dependencies. So you would use that one here and provide all the dependencies to it, and you can forget about it once for all.
Okay.
Okay, I think we should probably finish here and here because we are still like 10 minutes late. So thank you, everyone. And if you got any questions, please just catch me later. I'll be around. Thanks.